Hi, this is Dr. John Bergduff, and this is a video about linear models. So in the real world, it is often the case that there are quantities that relate to each other, where one quantity in some way depends on the other, meaning that as one value changes, the other value changes as well, perhaps in a predictable way. And sometimes that predictable relationship of changes can be represented by a graph or even an equation, and sometimes that graph or an equation might be a straight line. If that's the case, then you can create what's known as a linear model. And we're going to show an example of where that happens and how exactly to create that model. Now, this video is designed for the level of college algebra or high school algebra 2. It is not a statistics video. So if you found this video and what you were looking for was a video on linear regression, the statistical concept of linear regression, unfortunately this video is not what you were looking for. However, down in the description below this video, I have provided links to two videos by one of my colleagues, Shelby Bercu, that these videos really are about linear regression taught from a statistics point of view. So you might want to hop off of this video and check out those instead. They may be more what you're looking for. But if you're looking for a basic video on what linear modeling means at sort of the algebra level, this is the place for you, and let's go ahead and get started. Here is some data that shows the increase of population of League City, Texas since 1990. League City is a town in Texas halfway between Houston and Galveston. And over the years, it has grown from being a small little country town into being a fairly good size suburb of the Houston metro area. You can see here that I've got indeed two quantities that relate to one another. The first quantity is the year, and the second quantity is the population. And I've started down below that what is obviously the makings of a graph with a horizontal and a vertical axis, but with those axes marked off in special ways. The horizontal axis is representing years, and the vertical axis represents population. On this graph, I can represent the relationship between a given year and the population as a point, and in a sense get a picture that represents the data that I have. So let's do that really quickly. When I look at the year 1990 and a population of 30,035, that would be a point where the horizontal value would be 1990 and the vertical value would be 30,000, and that would give me a point right about there. 1995, 38,828, I can approximate that right here. Bear in mind, these are all approximations. This is not an incredibly accurate graph, but it's a good approximation. In 20,000, the population was roughly 45,000. Now you'll notice that I have the vertical axis marked off in units of 20,000. So 50,000 would be halfway between 40 and 60,000, and 45,000 would be roughly a quarter of the way between 40 and 60,000. Let's put that right about there. In 2005, the population was just over 60,000. In 2010, the population was 84,000. That's going to put me kind of about there, about a quarter of the way between 80 and 100,000. And in 2015, the population was just short of 100,000. Even putting these points on a plane gives us a much more visual understanding of the data that we have. It is very clear that the population is increasing over time, and if you look at those points, they almost or close look like they might match up with something close to a straight line. What I have drawn so far is sometimes called a scatter plot. This is a very simple one because in this case it's a function. Each value of the year corresponds to only one population, but if I plot the points that I have, they give me something of a a visual representation. I can make that visual representation more dramatic if I join adjacent points with straight line segments. That would create what we call a line graph. Now, a line graph does not mean you're drawing a single line, but what it does mean is that you're going to take adjacent points and join them with a straight line segment. And I'm going to do that right now. Joining adjacent points with straight line segments would give me something that looks like this. Definitely makes that more dramatic. I can see the relationship between all these points, and I definitely see that it does look a little bit like a straight line, not quite, but in that vein of being something like a straight line. Now, what I can do is I can say, since that does look much like a straight line, perhaps I can find a line that approximates this line graph really well. Ideally, we would like what we'd call a best fit line, the best possible line that most closely approximates this line graph that I have right now. That requires some tools from statistics that, again, we're not going to be talking about here. But even here, what we can do is simply pick a couple of the points and join them and look at the line that results and develop an equation for that. So what I'm going to do is I'm going to pick two of the data points that we have. I think I will pick the first year we have data for and the last year we have data for. That represents these two values in my chart, and it represents these 2 points on the plane. If I join those with a straight line, that will be approximately a good representation for the data that I've got. Hold on a second. All right, let me try this again. There we go. I'm even going to extend that line off farther to the right, because what I eventually want to be able to do with this model is use the data that I have to draw some projections or predictions about what's going to happen in the future. So I'm going to call that a linear model of what we have so far. Not necessarily a best fit, but at least it describes a trend. So I can also call it a trend line. What can I do with that? Well, because it's a line, I can find its equation. With the equation, I could make the predictions of where the population might be going in the future. Let's take a look at how that might look. So here's again just the table. I've taken the picture away. But I want to remember that what I'm focusing on is a trend line that was built from these two data points. And I'm going to write the equation of that line in terms of x and y. I'm going to let x represent the number of years since 1990, and y represent the population in year x. Now here's something interesting that we do. Frequently when we model change over time, rather than using, say, 1990 as our x value, we sort of set a year 0. If x represents the number of years since 1990, when I write 0 for x, that's referring to 1990. And so my ordered pair would actually be 0, 30,035. I'm leaving off the comma there because it would make it look like there's 3 numbers in that pair, which just doesn't make any sense. If I do that, when I look at another data point, and I'm looking at the value of x, what I have to think of is how many years is that since 1990. So I'm not going to use 2015. The number of years since 1990 would be 2015 minus 1990, and that represents 25. So 25 years later, in that year, the population was 98,179. So we have a line that goes through 2 points. When you have a line through 2 points, you can find its equation. You just need to do some work. First thing we need to do, and we've seen this in earlier places looking at lines, is we need to calculate the slope. Difference of the y's over difference of the x's. The second y value minus the first y value over the second x value minus the first x value. That tells me that the population has changed by 68,144. I think it's safe to put the comma back in there, over the course of 25 years. That also gives you really a concept of what this slope represents in this real world setting. The population changed by 68,144 people over 25 years. If we simplify that, which would give me 2,725.76, that's really telling me that the population increased by approximately this many people per year. Now, that number, we don't have 0.76 of a person, so as you see here in the instructions, we're going to round that to the nearest 10. That's frequently done. These models are only approximations, so they don't have to be perfect. I'm going to round that off to the nearest 10, and that would be 2,730. Now, that's the slope of that line. In addition, if you focus your attention on this first point again, notice that its x-coordinate is 0. When you have a point whose x-coordinate is 0, that means it is on the y-axis and is essentially the y-intercept. Let me go back to the picture and you can see that right there. That point on that line is the y-intercept. Because it's the y-intercept, in writing the equation, I could use the slope y-intercept formula, y equal mx plus b, where the m would be the slope that I just figured out, and the b would be the y-coordinate of the y-intercept. So that equation would be y equals 2,730x plus 30,035. That equation models the trend line for the data that we have, and furthermore, because it would be defined for any value of x, it's a tool that we could use to make projections into the future. Let's see what that would look like. So, going to the same data, let's use the trend line based on the population in 2015 that we figured out, and there it is, to predict what the population of League City, Texas would be in 2025. This would be a useful tool to have if you were a city planner and you were concerned about the needs of the city, perhaps roads, perhaps utilities, going into the future, knowing how to plan for continued growth. If you have this model, what you simply can do is plug in new values of x going off into the future. Now, the temptation is going to be to plug in the number 2025 for x. But we remember that x is the number of years since 1990. So the year we need to plug in for x is whatever the difference is between 2025 and 1990. That's 35 years, 35 years from the beginning of this study. So take this equation, y equal 2,730 times 35 plus 30,035. Do that calculation with a calculator or whatever, and you will discover that the predicted population is 125,585. So I have some data that relates to quantities. I can represent them graphically create a trend line, write the equation of that trend line, and very importantly, use that mathematical model, that linear model, to help project into the future, which is information that I might really need. So I hope this example was interesting, gives you a general idea of linear models, which you may study in more detail in statistics. I hope you've enjoyed it and have a great day.